All right, let's go. Number 10, the equation with no clock in it. In 1967, Bryce-DeWitt was trying to do something almost administrative. He wanted to take Einstein's general relativity and John Wheeler's quantum gravity work and merge them into one master equation, the way physicists had merged electricity and magnetism a century earlier. A tidy unification. Nothing more. Standard quantum mechanics assumes a background clock. Every equation you learn in a first-year physics course has a variable called yatsi, ticking forward, external to the system, always present. Schrödinger's equation without a t-term isn't really an equation anyone recognizes. DeWitt wrote down the wave function of the entire universe. He looked for the time variable. It wasn't there. The result is now called the Wheeler-DeWitt equation, published in Physical Review in 1967. When you apply the full machinery of quantum mechanics to the universe as a single closed system, the Hamiltonian constraint forces the time term to cancel out completely. Not approximately. Identically zero. Physicists tried everything. Some argued you just need an internal clock, some physical process, inside the universe you designate as time after the fact. That approach, called the Page-Wooters mechanism, works on paper, but nobody agrees on which physical process gets to be the real clock. Others assumed the equation was simply incomplete, missing some correction term future physics would supply. 40 years later, no correction has arrived. If the deepest equation we have for the whole universe contains no now, then the sensation you're having reading this sentence of a present moment sliding forward isn't in the fundamental description of reality anywhere. It's something added afterward, by you. So where exactly does now get inserted back into a universe that mathematically has none? The clock problem doesn't end with the universe as a whole. It gets stranger at the level of a single photon. Number 9, the eraser that shouldn't work. In 1999, Yoon-Ho Kim and a team at the University of Maryland were refining an old thought experiment John Wheeler had proposed decades earlier. Wheeler asked a simple question: does the way you measure a particle now change what it did in the past? Standard quantum mechanics says a photon behaves as a wave, interfering with itself, only when you don't try to know which path it took. Try to detect which path, and the interference disappears. That much was settled physics since the 1920s. Kim's team ran the experiment with entangled photon pairs and delayed the which path decision until after the paired photon had already been detected. Kim, along with Yu, Kulik, She, and Scully, published in Physical Review Letters in 2000. The interference pattern reappeared or vanished depending on a choice made after detection, correlated with data collected earlier. Careful analysis by the same physicists confirmed no signal, no information, travels backward in time, but the correlation itself required the later choice to make sense of the earlier data. Some suggested this proved retrocausality outright. That claim didn't survive scrutiny. Others insisted it was simply a subtle statistical artifact of correlation, nothing more. That explanation technically holds, but it doesn't make the discomfort go away, because the data only makes sense as a story once you know the ending. You are, at this moment, made of correlations that may only cohere once a future measurement occurs somewhere in your particle's history. Nothing here breaks causality. So why does the story of what happened only make sense once you know what happens next? If time isn't fundamental at the level of the universe's equation, some physicists asked where it comes from instead. Number 8, the temperature of time itself. In the 1990s, mathematician Alain Kahn and physicist Carlo Rovelli weren't trying to reinvent time. They were studying von Neumann algebras, an obscure corner of mathematical physics, looking for structure in how quantum systems evolve statistically. Ordinary physics treats time as a backdrop, something all systems move through identically, whether you know their exact state or not. Kahnes and Rovelli found that for a huge class of quantum systems, a specific flow, a kind of internal ordering, emerges automatically from thermodynamic and statistical properties alone, with no external clock assumed anywhere. They published Von Neumann Algebra Automorphisms and Time Thermodynamics Relation in Classical and Quantum Gravity in 1994. Their central claim: time may not be fundamental to nature. It may emerge from a system's statistical thermal relationship to its own state, the way temperature emerges from the motion of countless particles. This is not consensus physics. Most physicists treat it as a specific, unproven hypothesis, not an established result. Critics point out it depends on which statistical state you pick, and different choices give different times. Ravelli himself calls it a proposal, not a law. If Canas and Ravelli are right, the ticking clock on your wall isn't measuring something built into the universe. It's measuring a statistical relationship your body happens to be embedded in. If time is thermodynamic, what happens to it in a system with no heat to lose? That question leads directly to the one arrow of time everyone already takes for granted. Number 7. The glass that won't reassemble. Ludwig Boltzmann in the 1870s wasn't studying time at all. He was trying to explain why gases spread evenly through a container, a routine problem in statistical mechanics. Almost every fundamental law of physics works identically forwards and backwards. Newton's laws, Maxwell's equations, even the core of quantum mechanics run the same either direction on paper. A movie of two atoms colliding looks physically valid played in reverse. Boltzmann realized the arrow of time we experience has almost nothing to do with those laws. It comes from something else entirely: entropy, almost always increasing. Boltzmann's H theorem, formalized in 1872, showed that for large systems, entropy overwhelmingly tends to increase, not because of any time-asymmetric law, but because there are vastly more disordered configurations than ordered ones. A dropped glass has billions more ways to be scattered than whole. Physicists have proposed the universe simply began in an improbably low entropy state, without explaining why. Others invoke the multiverse, arguing our region just happened to start ordered. Neither answers the deeper question: why was the beginning special at all? Every memory you have, every sense of before and after, exists only because the universe started unusually ordered and has been forgetting that order ever since. If the fundamental laws don't care about direction, why does your entire lived experience run only one way? If entropy explains the arrow, some physicists asked whether the arrow could, in principle, run backward somewhere. Number 6, the influence that isn't supposed to exist. In 1986, physicist John Cramer wasn't trying to overturn causality. He was trying to solve a much older, narrower puzzle: why quantum mechanics needs two different mathematical waves, one going forward, one going backward, to correctly predict experimental outcomes. The standard interpretation treats the backward-going wave as pure mathematics, with no physical meaning, and causality as strictly one-directional. Cause always precedes effect. No exceptions. Cramer proposed the transactional interpretation. In it, the future measurement genuinely participates in determining the outcome, not as metaphor, but as a physical handshake between past and future. Cramer published The Transactional Interpretation of Quantum Mechanics in Reviews of Modern Physics in 1986. Under his model, a photon emitted here and absorbed there completes a real transaction across time, not merely across space before either event is finished. The interpretation remains a small minority position. Most physicists reject it because it appears untestable. It reproduces the same predictions as standard quantum mechanics, giving no experiment to distinguish them. Others object that treating the backward wave as physically real invites paradoxes the theory doesn't actually solve. If Cramer is right, some quantum event happening to you tomorrow may already be quietly shaping which outcome occurs in your body today. There's no experiment that can currently tell you whether this is happening to you right now. How would you know? Not every entry on this list is speculative. One of them was confirmed in a lab 5 years ago. Number 5, the crystal that never stops. In the mid-2010s, physicists at Google and several university labs weren't chasing anything exotic. They were testing whether Frank Wilczek's 2012 theoretical proposal, a structure that repeats periodically in time instead of space, could survive contact with the laws of thermodynamics. Most assumed it couldn't. Ordinary crystals repeat in space, atoms locked into a repeating lattice. A system that repeats in time, cycling forever without losing energy, should violate the most basic rule of thermodynamics. Closed systems settle into equilibrium and stop. In 2021, 2 independent teams built systems that did exactly that. They oscillated in a stable, repeating pattern indefinitely, without consuming or losing energy to sustain the motion. Randall and colleagues at Google Quantum AI, alongside a separate Stanford-led team, published confirming results in Nature in 2021, using a chain of trapped ions and a diamond-based system respectively. Both showed genuine time crystalline order, verified against rigorous theoretical criteria laid out specifically to rule out mundane explanations. Skeptics initially proposed the oscillation was simply externally driven, disguised as spontaneous. That objection was addressed directly in both papers through careful design. Others suggested measurement artifacts. Peer review at Nature didn't find one. You now share a universe with a confirmed physical object that treats time the way a crystal treats space, an object that literally cannot stop moving, by the laws of physics, without external interference. If a structure can be locked into time the way ice is locked into a lattice, what does that say about time's texture, and what else might already be locked into it? Time crystals are strange, but they still assume everyone agrees on the order events happen in. That assumption doesn't survive relativity. Number 4, the platform and the two lightning bolts. Einstein, in 1905, wasn't studying anything abstract. He was trying to resolve a genuine engineering-grade contradiction between Newtonian mechanics and Maxwell's equations for light, a problem bothering him since his student days. Newtonian physics assumed simultaneity was absolute. If two events happen at the same time for one observer, they happen at the same time for everyone, everywhere, no exceptions. Einstein found that assumption was simply false. Two events simultaneous in one reference frame can occur in a different order, entirely in another moving frame with no error involved on either side. In his 1905 paper on the electrodynamics of moving bodies, Einstein used the classic case: two lightning bolts strike either end of a moving train, simultaneous to someone standing on the platform. To a passenger on the train, one bolt strikes first. Both observers are correct. There is no error to fix. Physicists initially hoped this was some kind of measurement illusion, a quirk of light's finite speed rather than reality itself. It isn't. Every precision experiment since, including atomic clocks flown on aircraft, confirms the effect is physically real, not observational. There is no privileged true order underneath it. Somewhere in the universe, right now, there exists a valid reference frame in which events you consider your past and events you consider your future are reordered relative to each other. If simultaneity depends entirely on your motion, what does it even mean to ask what's happening right now, anywhere but exactly where you're standing? Relativity says order can shift between observers. Its own equations go further and permit something stranger still. Number 3, the rotating universe that loops. In 1949, Kurt Gödel wasn't working on cosmology as a specialty. He was a logician, a close friend of Einstein's at Princeton, exploring Einstein's field equations mostly as an intellectual gift for Einstein's 70th birthday. General relativity describes gravity as curved spacetime, and physicists generally assumed any physically reasonable universe would have spacetime curve in ways that keep cause before effect, everywhere, always. Gödel found an exact solution to Einstein's own equations describing a rotating universe in which certain paths curve back on themselves entirely, connecting a point in spacetime to its own past. Gödel published an example of a new type of cosmological solution of Einstein's field equations of gravitation in Reviews of Modern Physics in 1949. In his rotating model, a spaceship traveling far enough along the right trajectory could return to its own point of departure before it left. Physicists have universally noted our actual universe shows no observed rotation, so Gödel's exact solution doesn't describe reality as far as anyone can measure. Others point out closed Timelike curves also appeared near certain theoretical wormhole and rotating black hole solutions, meaning Gödel's result wasn't an isolated mathematical curiosity. Einstein's own equations, the ones confirmed by every gravitational test we have, mathematically permit your own timeline to loop back on itself somewhere in the space of possible universes. The mathematics doesn't forbid it anywhere in the equations. It just happens, as far as we can tell, not to be true here. Why not? If space-time can loop on the largest scales, some physicists wondered whether time might be granular on the smallest ones. Number 2, the second that isn't smooth. Researchers building loop quantum gravity in the 1990s, including Carlo Rovelli and Lee Smolin, weren't trying to redefine time at first. They were trying to quantize gravity directly. without string theory's extra dimensions, by asking what happens if space itself is chopped into discrete units. Relativity assumes space-time is smooth, infinitely divisible, with no smallest possible interval of duration ever. Loop quantum gravity's mathematics forced a strange consequence. If space comes in discrete minimum units, roughly the Planck length, time may come in discrete minimum units too, roughly the Planck time. Ravelli and Smolin, in papers through the 1990s, including their 1995 work in Nuclear Physics B, calculated a minimum unit near 5.4 times 10 to the negative 44 seconds, below which the very concept of duration may not apply at all. Some argue this discreteness is a mathematical artifact of the specific approach, not physical granularity. String theorists, working from a competing framework, get smooth time, and no consensus exists between the two camps on which if either is correct. If time comes in indivisible units, then the smooth, flowing sensation of your life passing may be an illusion built from something closer to a very, very fast slideshow. If time is made of discrete frames, what exactly happens in the gaps between them? Every entry on this list points at the same target. It's time to name it directly. Number 1, the now that may not physically exist anywhere at all. Philosophers of physics, working alongside researchers like Ravelli, weren't trying to unsettle anyone. They were simply asking what the Wheeler-DeWitt equation and relativity's relativity of simultaneity actually imply when taken together. Seriously, without flinching. Ordinary human experience assumes a universal, physically real now, a single present moment shared by everything, everywhere that moves forward together. Combine entry 10 with entry 4, and that assumption collapses entirely. The fundamental equation contains no time variable, and the equations that do contain time refuse to agree on which moment counts as now for different observers. This isn't a minority interpretation. It's a direct mathematical consequence of two of the most rigorously tested frameworks in physics, general relativity, and the constraint structure of canonical quantum gravity, taken exactly as written, with nothing exotic added. Some physicists respond that now is real for practical local purposes, useful at human scale even if not fundamental. Others argue the entire concept of the present moment is a cognitive construction, generated by a brain processing memory, with no counterpart in the equations at all. The moment you're in right now reading this sentence may not correspond to anything in the actual mathematical structure of the universe. It may be something only you and every other conscious observer are locally constructing. If now isn't in the equations, what exactly are you experiencing when you feel yourself living in it? The universe is not confused. The equations don't stutter and the mathematics doesn't hesitate. Every anomaly on this list sits not at the fringes of physics, but inside its most tested, most trusted frameworks, in the Wheeler-DeWitt equation, in relativity, in Boltzmann's entropy, in Einstein's own field equations. We are the ones without a stable place to stand. The universe runs on rules that never ask to be lived inside, one moment at a time, by something that insists on calling one particular moment now. If you want to see more videos like this, click the video on screen now.